there's about 40 or 50 of us, and Glenn is one of these members. And Glenn has been talking to us about glycosylation, but I thought his slides were great, and I thought you'd give a great talk. And so I want to show you everybody.
Okay.
So this is from Detroit, and these are all practitioners from Detroit, and these are super smart people, and we're all going to be interested in what you have to say, and I'll let you go. We got you up on a big screen right now, and we can hear you, so you guys take the stage, and why don't you introduce yourselves?
I'm Glenn. I work as a biochemist with the Thinks group that I share with David. My interest is really in cholesterol in the cell membranes, but also I've been looking at the role of sugar in the way it affects the cells working. I'm going to go into that in some detail in the presentation, so I'll hand you over to Sarah.
Hi, I'm Dr. Sarah Pugh, and I did a postdoc project on statins and caveoli in cardiac myocytes. I've just come here to listen in and join in if I'm needed.
Sarah and I did the interview which we were going to rely on in case this link didn't work, Just to introduce cholesterol to you in a different way to what you hear about it normally in medicine. It is basically existing in all the cell walls and all the membranes inside the cell, and it exists alongside fatty molecules, and they're in a ratio of 4 fat molecules to 1 cholesterol molecule. And all the structure you can see inside that cell, all those membranes are composed like that, plus in association with that you have the structural proteins which are interacting with lipid rafts. Now, lipid rafts are where cholesterol molecules strengthen the membrane a little bit to support functions that go on in those membranes. That's things like pores and channels and caveoli for functional things like exocytosis and endocytosis. And cholesterol was a really important development because there have been cholesterol-like molecules in our early evolution, and the prokaryotes didn't successfully integrate and form more complex eukaryotic cells like the ones we're made of until cholesterol was evolved, because cholesterol was the perfect molecule to moderate what's going on inside the cell wall. So there's a lot of cholesterol in there, and it's everywhere. So it somehow doesn't make sense to attack the way in which it is made, which is where we come in with the statin medications. Let's go to the next slide. My interest really got serious at this point. I was contacted by another Thinks member called Dr. Luca Mascatelli, who's a cardiologist in Italy. And he sent me a paper which has that rather complex title on that slide, Inhibition of Cholesterol Biosynthesis in Beta Cells. I must admit, when I first opened the paper, I thought, gosh, what a title. What does this mean? But it turned out to be the smoking gun that connected statins with type 2 diabetes. And what this paper was effectively saying was in experiments on human pancreatic beta cells and in experiments on mice, they could show that reducing cholesterol, like going down from a ratio of 20% to 18%, you can actually stop the functions of the cell wall from working. So endocytosis and exocytosis were failing in beta cells. And Luca issued me with a challenge. He said, do you think this happens in all tissues? And we went on to develop a thesis and a paper. And we did this by review process. So if we go to the next slide.
Yeah, we're there.
So we looked at this insulin release and found that insulin would be affected by statins. And that was one of the things that was being reported. We looked at 7 clinical trials, and of the 7, 6 reported poor glucose control. Trial number 7 didn't mention glucose at all. They didn't look at it. Or if they did look at it, they chose not to release the data. So we have a smoking gun for the type 2 diabetes being caused by the statin. We then thought, well, what's happening in other tissues? And we went on to the PubMed databases and we looked at bone remodeling. We knew that statins were being trialled for treatment of osteoporosis because they stop loss of calcium from the bones, which is one of the features of osteoporosis. And I dug a bit deeper and I found that we could actually find papers reporting microfractures on long-term statin use. There was one particular study on postmenopausal women in Turkey, which was particularly interesting. They were coming in with vertebral microfractures. And then we started looking at this more detail, and it seemed to be that the osteoblasts, which were responsible for repairing the bone, and the osteoclast, which was supposedly taking away the poor older bone structure, were both inhibited by their inability to carry out endocytosis and exocytosis in the maintenance of the bone. So we were looking at a situation where there was no bone remodeling going on. The stoppage of the calcium loss was correct, but there was no repair to the fractures. We then went on to look at neurons, which are perhaps a bit better studied, and there's the work of Frank W. Frieger involved in this, who's a European biochemist who was the guy who pointed at cholesterol as being the one that was involved in synaptogenesis. When you look at the nerve, it's protected by a wrapping of myelin, which is all around it, like the plastic coating on a wire. Myelin is 50% cholesterol, and you can't make and repair myelin without cholesterol. And there were studies where people were attempting to use statins to fix multiple sclerosis. That was a crazy idea. That didn't go very far because it was preventing the repair of the myelin. And then you had the synaptic junction where the neurotransmitters were being released in the pods to go across to the next neuron in the chain. A lot of cholesterol is involved in wrapping those neurotransmitters and releasing them. And there was the action itself, which relied on the cholesterol in the membranes to facilitate that release and receipt of those things going across. So neurofunction fundamentally dependent on cholesterol. If you ask yourself how much cholesterol you've got in your body and where is it, the brain, 5% by body weight, contains 25% of the cholesterol. So clearly it's important. We also looked at behavioural problems. Violent death studies were showing that there was a lack of cholesterol and fats in the cerebrospinal fluid. We noticed that there were reports of aggressive behaviour as well in people who were on statins. So there's clearly a lot going on in the neurological system about this. When the nerves actually meet the muscle, the neuromuscular junction, there's a problem there because the receptors on the muscle are receiving messages wrapped in cholesterol from the nerve ending. So you've got this neuromuscular junction. It's really not functioning correctly. Duane Graveline, space doc as we all know him, he suffered particularly from this problem. He knew he had conductivity in his nerves. It had been tested. He knew his muscles weren't responding to nerve impulses. There was a problem where the nerve joined onto the muscle, and Duane gave us a few clues on that one. So we've got that muscle function, we've got the synapse, we've got the memory, neuromuscular junctions. Going back to some work that Luca had done on cholesterol, we looked at immune function, and particularly an interesting one was looking at our front line, which is the skin. The skin is such an important barrier to the outside world, and it's protected by the release of fatty substances from the sebaceous glands, and they are full of cholesterol and cholesterol dependent, and that whole business of protection coming from that is about cholesterol fogging the bacteria that live on the skin. And Luca had already published on this subject, showing that statin patients were more prone to infection from MRSA, and that whereas healthy people could fog the MRSA. I mean, if there's a lesion in the skin, they tend to party. You know, there's food around, so the bacteria is going to party mode. I'll just summarise quickly on this next slide, cholesterol's role. So we talked about cell wall integrity, form and function. Okay, which is, we know that it is a wrapper for things that are moving around in the blood. We know it's packaging for neurotransmitters. It's always good, it's never bad. And of course it's an intermediary in the production of a lot of steroids as well. An interesting paper that cropped up after we'd published that was the one from Thomas Haynes. Again, Duane Graveline actually pointed us at this one. And this one shows that if you lower cholesterol in the membrane, it leaks. It leaks seriously. So if it's a nerve, it will leak its activation potential and not fire correctly or fire in the wrong direction. If it's a muscle, it will break down and the muscle cell contents will eventually clog the kidneys, causing rhabdomyolysis and so on. Thomas Haynes published it under the title "Do Sterols Reduce Protein and Sodium Leakage Through Bilipid Layers?" Be very careful in this title to avoid criticising statins, because at that time, if you criticised a statin, you weren't going to get published. You know, it was just taken as read. Everybody knew that statins were going to fix the cholesterol problem, and you couldn't get through. I have a bee in my bonnet about calling lipids cholesterol. We know cholesterol is a molecule. It's not good, it's not bad, it's a single molecule. So when we use the word cholesterol when we really should be using the word lipid, that's a bit confusing because it gives credibility to the idea that if you prevent the production of cholesterol, you will fix the problem of high cholesterol as it is thought to be. I've got a very different explanation to this, which I will come up with now. On this slide, we should be looking at a tube containing some lipids. It's a spin down from a centrifuge of a blood sample. The point being that if you're talking about LDL and HDL, and all the various umpteen fractions of lipids in the blood, you should use the word lipid, not cholesterol, because cholesterol is just one player in among the protein and all the other stuff. And I always take it that when someone talks about good and bad cholesterol, I always challenge them on this issue because it puts them on the back foot, and you find out whether they know why they're there in the bloodstream. These particles are not there trying to kill us. The fatty nutrient cycle. So what we've got here then is a very simplified diagram. It's not quite as simple as this diagram suggests, but between the liver, outbound to feed organs of fatty nutrients, we get the formation of LDL. And LDL is characterised by size, and it's characterised by the protein label. And organs can select LDLs and absorb them with the fatty nutrient package inside. They send back fatty rubbish from that process by releasing it back into the bloodstream. So oxidised cholesterol and various fats, which are being returned for recycling or disposal, come back in the bloodstream as HDL particles. And when this is working correctly, there is a ratio of something like 5:1 of LDL to HDL. The LDLs are heavier, so the 5:1 ratio roughly corresponds to the difference between full packages going out to feed the organ, the LDL, and the HDL bringing back the rubbish for recycling. That's a functioning nutrition cycle. If we look at this one now, this is just representing the fact that we now have damage to the LDL particles or the LDL receptor mechanism. And so the LDL is now unconsumed. Because we're not taking LDL into the organs, we're not sending HDL back on the return side. So you see a change in the ratio now. LDL goes up and HDL goes down. So the ratio is important. I'm not sure the total is very important, but the ratio certainly is. And when you see HDL disappearing and LDL building up in the bloodstream, that is a sign not that we're making too much cholesterol. It's not a sign that we are making too much lipid. It's a sign that the lipid is not being consumed. Now, the pharmaceutical solution to this is to not make any more cholesterol. But we have a fat-starved organ out there, and it's not getting fed. And the guilty party for that damage is, of course, our little molecule glucose and fructose. They are reactive sugars. AGE is an acronym for Advanced Glycemic End Product. It's rather good to just call it AGE because as we get older, the amount of accumulated sugar damage on our proteins increases faster than our immune system can clean it up. So we get a lot of aging of proteins. There is a mechanism within the immune system for fixing this, which leads us into rage. That tends to be an inflammatory process whereby the immune system is cleaning up on age. So there is a receptor within the immune system for cleaning up the damage. And you're looking at some of the implications of this on the other panel. We've got possible insulin resistance due to aging on the receptors. We've got elevated blood pressure due to aging of elastins and proteins in the blood vessel. Immune cell deficiencies because of being damaged by the sugar. A loss of skin appearance and elasticity. Joint inflammations and so on. Those are all the things that you're familiar with as medics, which are happening as a result of sugar damage. And Stephanie had read the original paper about lowering cholesterol and it being ubiquitous and in its damaging effect on all cells in the body. And she invited me to collaborate with her on if it wasn't the cholesterol that done it, we're going to now be pointing the finger at the sugars, and we wanted to know if that was correct. So we started doing reviews again on public medical database of how metabolic syndrome was affected by sugar damage. It was quite straightforward, really. I mean, there's loads of evidence out there, but what we are seeing, of course, is if you control HbA1c, which is the measure of sugar damage in the blood, it's a measure, the hemoglobin protein is sugar damaged, and we count, I think you may use a different scale in America. Do you use the millimoles per mole on HbA1c, or the percentage?
Ours is percentage.
They're closely related. We wouldn't say 8%, we'd say 80 millimoles per mole. Basically, you're counting the number of blood protein molecules, and you're seeing what proportion of them is damaged by the attachment of a sugar, which will modify them. What we see is that a lot of these conditions, they do improve with the control of the sugar and the attachment. One thing I should say about sugar at the moment, because you notice I'm talking about fructose a lot here, is that fructose and glucose behave very differently. Fructose is a much more reactive molecule in the bloodstream than sugar. We are told that fructose is not a player in the bloodstream, because when you're at medical school you presumably learn that the liver goes to a lot of trouble to remove fructose from the bloodstream. Well, this was true until recently. In about the late 70s, when we started putting more fructose in the diet, we began to overwhelm the ability of the liver to remove fructose from the bloodstream. That had an upper limit, apparently. Bjorn Hammarskjöld, he's a senior paediatrician, he tells me that the upper limit for that is 15 grams per day. That 15 grams per day is easily exceeded by modern diets. So if you had a few large colas with fructose in them, you might take 60 grams in a day. So you're giving your liver 4 days processing to get rid of that fructose. The other interesting thing to note about fructose is that it is more reactive. So it is going to attach to proteins more aggressively than glucose. But we are putting a lot more of these products in our diet. We also looked at the things like amyloid. The amyloid is there as a pinch hit, I think is the phrase you use in America, for cholesterol. If you deplete cholesterol and cells become leaky, that's bad news for a neuron. So the neuron is going to start making beta amyloid to plug the gap as an emergency sticking plaster mechanism. And then, of course, eventually, because the neuron's in trouble, it will die, and the amyloid will be released in a form of a plaque. We were seeing this in the literature. So we weren't surprised when we heard that they were pulling products from the pharmaceutical trials which were attacking amyloid production, because they were disappointed in their results. In fact, they were making matters worse, because the amyloid was there to do a job, substituting for cholesterol, which had been depleted by the use of the statin. So we had a little vicious thing going on there between statins and the neuron function. I'll come on to central visceral fat as well later on. All cholesterol molecules are important. Blocking cholesterol synthesis is damaging. The poor lipid profiles will improve if you control the HbA1c. Do bear in mind that we may be looking at a fructose crisis as well as a glucose crisis. I don't think anyone's really... Basically, I would propose that we have a triad of issues in modern medicine. Decades of excess blood sugars and all the damage that's caused to the lipid mechanisms, and the damage to the proteins in the body, such as stiffening of the arterial linings and so on, which is affecting blood pressure. Sarah and myself have been discussing recently the possibility that there's a wider implication for a lot more receptors in the body, including thyroid and hormones and all those sort of things. We've got the decades of low-fat foods because we've been taught to fear fat, so we've had inadequate lipid nutrition anyway. And then we go in and lob a grenade into the liver and say you can't make any more cholesterol, so we can't even package the lipids properly now, and we're seeing a crisis from that. So that's the statin damage triad, and I would propose that as quite a serious problem for the medical profession at the moment. Let's move on to look at the start date for all this. And we are looking at a start date which corresponds to the end of the 70s, where up until that point obesity was running in the population at roughly about 3%. I remember being at school and in a class of 30 people, one person would be slightly overweight. 5% obesity rate was normal. Suddenly it climbed. What did we do at that point? How did we bring this about? I think when you look at what was going on at that time, there was an introduction of fat phobia. We were being told eat less fat, eat more carbohydrates. We had that famous pyramid being published by Senator George McGovern, and that went right round the world, the food pyramid, telling us to eat more grains and eat less fat. And he was representing Midwest farmers, of course, so they had a lot of corn to sell at the time. But if you look at several mature onset diseases, they all seem to kick off at that point. So that what's true of obesity is also true of diabetes. We really are looking at an event in our history. There are molecules in proteins called lysine, which are an amino acid. They are vulnerable to chemical attack by sugars. This process is slow. It's the sort of thing you see when you cook. Browning reaction in the oven is very much an age production where the proteins and the sugars are joining together to make really tasty food. And don't worry about eating them because they get broken down in digestion. But we've got this process going on. We've got the immune system's response to it. That's quite interesting. We've got the nuclear factor kappa beta, and we can get something called a cytokine storm in those circumstances, whereby the immune system tend to overreact, and then you'll start noticing it because things will start to ache. So you'll notice a lot of joint pain and a lot of inflammation in the ends of muscles, the tendons, and so on. The parts of the body that are made from proteins, the jelly bits, they tend to inflame if you get sugar attachment, and the immune system tries to clean it up. And that immune system reaction may lead to actual damage of things like ligaments and so on. I think you'll find that if you look at the epidemiological evidence, that too kicked off in the late 70s. We've seen a lot more of those problems in the last few decades. Talking with Sarah on email, and we were discussing something called the Randall cycle. Your body makes a choice between fuels. It will either burn sugar or it will burn fat. It can't do both at once. Glucose, if it's burnt for producing energy, that's fine. That's what it's for. That's about all it's useful for in the body. There's a very small percentage of glucose and sugars required in diet. There's a very tiny amount in your body anyway. It's percentage-wise, sugars are not very significant. There are a lot of sugars involved in organ membranes, in the glycocalyx and so on, but they're structural sugars. They're not really players in terms of cruising around the body and causing damage. Excess glucose. We tend to eat too much. So what do we do with the excess? Well, it's quite simple. You save it for a rainy day, don't you? Your body releases the fat hormone, drives fat production, which is insulin, and it converts it to glycogen and eventually persuades the body to convert that into fat. Probably end up in the subcutaneous fat. Body is now being challenged to store more fat than it's got room for, so subcutaneous fat builds up. I mean, you can't store an endless amount of fat. Sugar is now being pushed into visceral fat cells, are in the abdominal cavity, and so after subcutaneous fat is full, you get visceral fat build up. After visceral fat build up, you get any excess pushed into the liver, because the visceral fat will eventually fill up and the liver will develop fat. If we try to unwind this fatty liver condition, we need to switch to a particular process called fat burn rather than sugar burn in the body. Remember when we were talking, I mentioned the Randall process. Randall gives us a choice as to whether we're burning sugar or burning fat. The body will burn sugar every time you give it plenty of sugar. But if you reduce the amount of sugar, the body will adapt to burning fat. This is going into a fasting mode. Burns sugar after a meal when you're satiated and there's plenty of sugar in the bloodstream. But if you can reduce the sugar from the bloodstream, your body will switch to mobilizing the fat to make sugar, a ketogenic sugar, and it will burn the fat to do that, to give that supply. Fortunately, the body chooses to do it in the reverse sequence, so it will remove liver fat first if you go to ketogenics, and then it will remove visceral fat, and then it will start using subcutaneous fat, although by that time you're probably got enough fat in your diet to provide your energy needs straight from dietary fat sources. although you can actually remove subcutaneous fat by being severely ketogenic as well. What improves with a low-carb lifestyle if you actually try and reverse this process? Now that's quite an impressive array. That's come from the Diet Doctor website. We could probably add to that as well, because there's a lot of interest at the moment in the role of sugar in driving tumours. There's a trial started on reducing sugar in association with certain cancer treatments, which are looking at PIP3 kinase, which is the enzyme that's activated by insulin. Tumours don't have insulin resistance. When you produce insulin as a type 2 diabetic, and if you happen to have a tumour in you, that will drive it crazy, because the insulin is available to drive the tumour, even though you are actually insulin resistant in the rest of your body. That's an interesting one to watch. The PIP3 kinase treatments have been a little bit disappointing in some kinds of cancer, but by combining them with a low-carb diet, which is taking people into ketogenesis, there are actually evidence that tumours will reduce. There's a lot of anecdotal evidence here, and now we're seeing serious clinical trials being conducted. How do we get people to change their behaviour? Well, we need to educate them about the sugar in food. So I've got a set of interesting infographics here, which basically show you the relative sugar content of foods. You know, the first one on fruit, if we're looking at that, is about bananas being top of the scale, and things like apricots and strawberries and berries generally are remarkably low in sugar. You know, blueberries, strawberries, there is sugar in there, but you know, you can have a reasonable portion without overloading yourself on sugar. The next infographic is a particularly interesting one on breakfast, where we're looking at a typical cornflakes with milk and brown toast. That is an extraordinary slide. The portion of cornflakes there is 30 grams. Now, I've taken a dish of cornflakes that I've seen people, you know, and weighed it, and most people choose about 90 grams or more in a dish of cornflakes. So they're actually eating 3 or 4 times that amount. And bearing in mind that 1 spoonful is what's circulating in the blood, that's quite a dramatic excessive input of sugar into the blood. Quite a lot of sugar in relation to what's circulating in the blood in any one time. Apple juice is a particularly tricky one. I mean, most people think of apple juice as being quite a healthy drink. Just a 200ml shot of that is going to cause some serious problems. If we look at cereals, again, you can compare cereals on that one. I don't think there's much good news about cereals, really, if you're trying to avoid sugar. And then finally on the infographics, we're comparing different types of bread. Again, we know that wholemeal bread is slightly better than white bread, but in the end of the day, it's still going to spike your sugar. We've got some behavioural changes that we can make by giving people instructions on making better food choices and leaflets that we give out. Interestingly, on low-carb leads, we've had a lot of people going into diabetes remission. A guy came to us last September. He was going on to insulin. After he'd been with us for 3 months, he was told he was no longer diabetic. So he'd lost 3 stone in weight, and his HbA1c had come down from roughly about 8.5%, is it, to something a bit more reasonable, like 4%. We've only been going since October, so we're really pleased to see those kind of results in such a short timescale. And we asked doctors, you know, have you ever seen this happen in your practice?
Yeah, everyone's shaking their heads yes for that.
Yeah, I knew your practice would have seen them. One of the things we've noticed on low carb is that you get increased loss of fluid from the body, because the fluid is associated with storage of glycogen. So, you know, lose 7 pounds in 7 days is typically a glycogen figure, where you lose about 6 pounds of water along with a pound of sugar. You also have the effect of insulin on fluid retention, and of course as soon as you start losing fluids, you're going to start losing water soluble substances from the body. You might know better than I do whether in fact this can have an impact on the B vitamins seriously. I do know that you can see riboflavin leaving the body. It's quite spectacular, really. And I've got into a little bit of a research review with Dr. Bjorn Hammarskjöld in Scandinavia. Last autumn we were having a discussion about it. Guidelines typically in countries in Europe say about 6 grams a day should be the maximum amount of salt you take into the body. Bjorn is quite upset about that number, because he's noticed that this is exactly the number below which you tip over into needing to retain sodium in the body. If you go below 6 grams a day on salt, sodium retention becomes a priority for the kidneys. If we go below 1 a day to replace what we've lost through urination, we are going to trigger a process where the kidneys will release renin, to release angiotensin, to release aldosterone, to put the blood pressure up, and that allows the kidney to recover more sodium from the urine. Angiotensin is a player. What tends to happen with elderly people is that they lose water, they lose salt, their kidneys put the blood pressure up. You then put an angiotensin conversion enzyme inhibitor in to bring their blood pressure down. The kidneys can no longer retain the sodium. You have a serious crisis, and there are reports on the public medical database of serious casualties through loss of fluid and salt in elderly people who are not feeding themselves properly and not able to look after themselves properly in this respect. So there's going to be a research review paper from Bjorn and myself and a few other players about this. Who's adding the salt? We have to remember that if we persuade people to eat real food and come away from the processed manufactured food, they become responsible for adding the salt in, which, as we know, is vital to good health.